Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics, and we are going towards the end of the lecture series on semiconductors, and is the last chapter, and in this lecture 13 we will be dealing with the following aspects with a view to obtain the rectifier equation. There is a rectifier when you combine p and n type material, or when you get a p-n junction, the p-n junction acts like a diode. It is a junction diode equation, that is what we have to obtain. So, the contents are expression for the width of the p-n junction, extension of the ionic layers depending upon the bias, the junction diode equation which is to be obtained finally. As I told you earlier, in order that you recall what I told in the last lecture, I show the p-n junction when you combine the p type material with the n type semiconducting material, you get the so called the depression region in the center of the p-n junction, which consists of immobile ions of both negative and positive charges, and this is the potential profile. What do you understand by potential profile? This is the opposing potential that an electron has to overcome or a hole has to overcome when it goes from one side to the other side. The electron will try to go from the n to p, and excess holes are on the p side, and the hole will try to go from p to n. Whatever be the case, whether it is electron or the hole, the potential profile or the potential barrier which it has to overcome is given by diagram of this kind, wherein we stated that theta 1 is the potential here and theta 2 is the potential here, and this theta naught, as I mentioned briefly in the last lecture, it is called the contact potential, sum of theta 1 and theta 2. The potential with its reference 0 potential at x equal to 0 is called the contact potential, that is here it is 0 and here it is theta naught, that is called the contact potential. Therefore, I write theta naught is equal to theta 2 at which point at x is equal to x p plus x n, that is the point at which I evaluate theta 2, that will be equal to theta naught, the so called contact potential, and that will be equal to the expression of this kind, which obviously will be getting. This is the continuation of what we have seen in the previous lecture. It consists of an expression of this kind, E times N d into x p plus x n. What is x p plus x n? The width of the depletion region to the power of 2 by 2 epsilon plus E into x p is the width of the ionic layers in the p side by epsilon into N a plus N d. You know, N a is the number density of acceptor atoms and N d is the number density of donor atoms multiplied by again the width of the depletion region, that is x p plus x n minus E times x p square by 2 epsilon multiplied by N a plus N d. That is the expression for the contact potential. In the above equation, x p can be expressed in terms of the total thickness of the depletion region by noting that at x equal to or greater than x n plus x p, the n type material is neutral and therefore, the associated electric field is 0. So, therefore, I can differentiate theta 2 with respect to x and make it to 0. So, d theta 2 by dx at x is equal to x p plus x n will be equal to 0, because the potential becomes stationary after x p plus x n, the potential becomes constant. That will be equal to minus E times N d into x p plus x n by epsilon plus E into x p by epsilon into N a plus N d. Because the whole thing is equal to 0, these two can be now equated. One of the terms can be taken to the other side and this can be simplified. This turns out that x p, that is the extension of the ionic layers in the p side, will be equal to N d by N d plus N a into x p plus x n. That will otherwise be equal to x p into N a plus x p into N d, that will be equal to x p into N d plus x n into N d. This will become equal to x p into N a into x n into N d. X p and x n are the width of the ionic layers in the p side and x n is the width of the ionic layers on the n side. Supposing N a is large, what will happen? Assume this right hand side to be some constant, right. Whatever be the value that will be assumed by the right hand side, if N a is large, if you make the number density of the acceptor atoms to become very large, then what will happen to x p? X p should automatically decrease. If you assume this right hand side to be a constant, if N a is continuously increased, then x p should automatically decrease. This is a very important relation. So, whenever large doping is made or the doping is continuously increased, the width of the ionic layers will start decreasing. That is very important, right. So, when N d is made very large, x n will become much smaller compared to x p. This means, when the n region is heavily doped, the ionic layers extend deeper into the p region. So, if you look at the last expression, keep on increasing N d, right, the donor impurity atom, you are adding more number of donor atoms, the x n will decrease. X n decreases means what? X p will be increasing. The doping concentration, when it is very small, then the layer thickness on that region will become much larger. This means that when the n region is heavily doped, the ionic layers extend deeper into the p region. Again I will repeat, when the n region is heavily doped, when the n type region is heavily doped, then the ionic layers on the p side will become larger. It extends deeper means it becomes larger. This leads to a very important conclusion, namely the depletion region extends deeper into that region which is leastly doped. This is very important, a very important consequence that we are obtaining from the above equation. That means, the depletion region extends deeper into that region which is leastly doped, or in other words, if it is highly doped, then the depletion region will become much smaller. The above equation also shows the equality of charge transferred from donors to acceptors, substituting xp in terms of xp plus xn from the relation for xp in equation for theta naught equal to theta 2, it leads to theta naught to be E by 2 epsilon into Nd into Na by Nd plus Na into xp plus xn to the power of 2. That is the expression for the contact potential, the total potential that I showed in the potential profile, or this can be shown, the width of the depression region can be shown now. The width of the depression region, that is you have got xp plus xn, that is the width of the depression region, right. That is a very important factor, that xp plus xn will become equal to 2 epsilon into theta naught by E to the power of 1 by 2. This part is not of very great relevance, whereas the second part has got lot of bearing, it carries lot of significance, wherein you have got Na plus Nd in the numerator and Na into Nd in the denominator, the entire thing raised to the power of 1 by 2. What does it mean? Now, what will happen to the depression region if you increased Na and Nd? Supposing you increase the number of donor atoms as well as the acceptor atoms, that means if the doping concentrations are increased on the N side as well as on P side, right. On the N side means you are adding more number of donor atoms, that is the N side. The P side means you are adding more number of acceptor atoms. If both Nd and Na both are increased, you note that Na and Nd come in the denominator, right. So, when Na and Nd are made larger and larger, what will happen to xp plus xn? The value of xp plus xn will start decreasing. You see that Na and Nd, the product comes in the denominator, the summation comes in the numerator. When compared to summation, the product will carry more weightage, because Na and Nd, the product comes in the denominator. When Na and Nd are made much larger, you keep on increasing Na and Nd, then your xp plus xn will become smaller and smaller, leading to what is called the Esaki diode. When the doping concentrations on both sides are increased, then the value of xp plus xn will become very small, the width of the PN junction will become very small. That is what was shown by Leo Esaki of Japan, for which he was given the Nobel Prize, because it led to what is called the Esaki diode or the tunnel diode, right. We have got tunnel diodes, right. We have been considering so far the normal PN junction. If the doping concentrations are increased on either side to a very large extent, then the width of the barrier will become very narrow. What is the meaning of width becoming narrow? Whenever you got a potential barrier, when it is very narrow, what will happen is you can think of the barrier penetration. You have the electron or the hole that can penetrate, because the barrier width is very narrow. When you have got a very broad width of a barrier, tunneling will not be possible. So, you come across what is called a tunnel diode or Esaki diode. What is meant by tunneling? What is meant by tunnel diode? A tunnel diode is nothing but a heavily doped PN junction. If you have got a p type material being combined with n type material, if the doping concentrations are increased to a very large extent, then the width of the PN junction will become very narrow. I told you, when the PN junction is heavily doped, that is both p side and n side, if the doping concentrations become very large, you dope the p and n to a very large extent, that is the number density of acceptor and donor atoms are made very large, that means the denominator becomes very large. Okay. If the denominator of expression becomes very large, obviously the whole thing will decrease, that the width of the depression region will become very small. That is what was observed accidentally by Leo Esaki. That led to what is called the Esaki diode or tunnel diode. Hence, if the doping concentrations on either side are increased continuously, it will lead to a decrease in the width of the depression region, ultimately leading to what is called a tunnel diode, or the same diode named after Leo Esaki, who found the so called tunnel diode or Esaki diode. Okay. A heavily doped PN junction will have a very narrow potential barrier. The width of your PN junction will be very narrow, so as to allow tunneling of electrons. They call it tunnel diode because now we can think of electron as a equivalent de Broglie wave. The electron is considered a wave, it can tunnel through the barrier. That is the reason why it is called tunnel diode. The electron can tunnel through the barrier, right. It need not overcome, it need not go over the barrier as it happens in a normal PN junction. It is a heavily doped PN junction. In a heavily doped PN junction, the width becomes so narrow, so that you can expect tunneling. You have in solid state physics tunneling in very many regions. The Cooper path tunneling, Josephson tunneling, and tunneling of alpha particles, and now you have the tunnel diode or Esaki diode. So, tunneling is a quantum mechanical phenomenon. Now, it can be present only if the width of the barrier is very narrow. Now, in the case of PN junction, you can eventually obtain a very narrow width by doping heavily the p side as well as the n side. If both sides are heavily doped, the impurity atoms are added to a larger extent on both p side and n side, the width of the barrier will become very narrow. When the width becomes narrow, tunneling is possible. The electron need not go over the barrier, it can tunnel through the barrier, because the electron assumes a wave like nature. So, tunneling can be present only if the barrier width is very narrow. Such narrow barriers can be obtained by increasing the doping concentration. So, a heavily doped PN junction will have a very narrow potential barrier, so as to allow tunneling of electrons, and this forms the basis of tunnel diode, which is now being presently used as oscillators, high frequency oscillators. So, tunnel diodes are used. It was observed by Leo Esaki from Japan. Now, we have shown that there exists a contact potential theta naught across the PN junction. Now, we can proceed to obtain the expression for the current which will flow across the PN junction for various voltages. What is it we are going to do now is to bias the PN junction. You are going to apply forward bias or a reverse bias. You are going to bias the PN junction. By biasing, what will happen is the width of the PN junction will become either larger or smaller. Okay. The width of the PN junction will become larger or smaller depending upon the nature of the biasing. Depending upon nature of biasing, the potential it has to overcome also will obviously will become large or small. Okay. So, when no external voltage applied, as I showed you in the previous lecture, when no external voltage is applied to the PN junction, the total current will be equal to 0, I 1 plus I 2 plus I 3 plus I 4 is equal to 0. Now, what is it we are going to do now? We are going to find out the currents I 1, I 2, I 3, I 4 when you give the PN junction a forward bias. If the PN junction is biased positively, the forward bias, then what happens to I 1, I 2, I 3, I 4? Similarly, when you reverse bias, what happens to these things, and then we have to find out the total current. I 1 is assumed to be the whole current from P region to the N region. you have got holes at the p side, they try to go to the n region. If p p is the equilibrium hole density in p type material, only those carriers whose energy is equal to or greater than E theta naught, the potential barrier will be able to go to the other region, leading to a current I 1 is equal to C 1 times P p into e to the power of minus E theta naught by k t. What do you understand? I 1 is the current which is due to, you have got the hole density is P p, right. One p refers to the p type, the other p refers to the holes, right. Suppose I write p suffix n, it refers to the electrons in the p side material. If I write p p, that means holes in the p type material, right. If p p is the equilibrium hole density in the p type material, only those carriers whose energy is equal to or greater than E theta naught. What is theta naught? That is a potential barrier which will be, then only the hole can go from the p side to the n side. And what I mean by this is, you look at the diagram again, the potential profile, you will see that theta naught is the contact potential. A particle will be able to go from here to here only if its potential is raised above theta naught, because theta naught is the height of the potential. The particle has to go from here to this region after x p plus x n, right. The theta naught is the contact potential, they have to overcome a potential barrier of height theta naught. What is the potential barrier? When a car goes in a road, you come across a bump, right. It has to, the car has to overcome a potential barrier, it has to go over the barrier, right. Supposing there is what is a potential well? A well in a house where you have got water, it is a potential well, because it is attractive potential, right. It is in the downward region, right. There is a potential, below this it is a negative, means it is a potential well, which I will show later. Now, this is a potential barrier, right. You have got a particle here, when all the way it has to go up, right. It has to overcome a barrier of height theta naught. So, the amount of electrostatic potential is E theta naught, E is the charge, E theta naught will be the barrier which is experienced by the particle. So, only those particles which have the energy will be able to cross over, that is the number of among p p, the number of holes which will be able to go to this region from p side to n will be given by e to the power of E theta naught by k t. What is E theta naught by k t? Where from you are getting? You write in classical statistics e to the power of minus w by k t. Same way you have theta naught is the height of the barrier and k is the Boltzmann constant, T is the temperature at which all these things are happening. So, you got a negative exponential as you write in the case of classical statistics, you write e to the power of minus e times theta naught by k t. Okay, this is the I 1. A similar expression will be there for the majority carriers. I 2, what is I 2? It is the number of electrons, small n refers to number of electrons, which try to go from the n side of the semiconducting material. From the n side it tries to go to the p side. This is the number density of the carriers in the n type semiconductor. I 2 is the electron current from the n region to the p region. If n n is the equilibrium electron density in the n type material, n n is the number of electrons in the n type material, then similar to the earlier equation we can write a corresponding current contribution. You write I 2, they are the two currents are the majority carrier currents, right. They have to overcome a barrier, right. You should remember they have to overcome a barrier. On the other hand, suppose a minority carrier comes, what will happen? A minority carrier, suppose it comes, ionic layers present, suppose a hole comes here, you know the majority carriers are here are holes, right. Suppose a hole is coming here, it will be opposed by the positive ions. Similarly, when electron comes here, it will be opposed by the negative ionic layers. On the other hand, they are the majority carriers. Now, what about the minority carrier? The minority carriers which are not shown here, the electrons are minority carriers. Suppose an electron comes here, what will happen to the electron? You think about this problem. Suppose electron comes here, what will happen? These electrons will be attracted by the positive ionic layers, right, because a negatively charged electron will be attracted by the positively charged ionic layers. So, the presence of the positively charged ionic layers on the n side will act like a potential well for the minority carriers. So, you should remember the most important point, the presence of positive ionic layers on this side will act as a potential barrier for the holes, the majority carriers, the holes are majority carriers, the majority carriers will be repelled by the positive ionic layers. So, this acts like a potential barrier for the majority carriers, whereas for the minority carriers, namely electrons, they will act as a potential well. The electrons will be attracted by the ionic layers because they are positive charge. Similarly, if an electron comes here, this region, that will be attracted by the ionic layers. Therefore, you should bear in mind for the majority carriers, the ionic layers which are present, they oppose the flow. So, they act like a barrier. For the minority carriers, the depletion region, the ionic layers act like a potential well, right. This is a very important point. So, it is a potential well means what? The current for the minority carrier depends upon what? How many ionic layers are here, or what is the number density, right. If more number of negative ions are there, then the force experienced by the positive hole, the force experienced by, you have a hole here, supposing a hole comes, supposing the electron is a minority carrier, right. The holes are majority carriers, electron is a minority carrier. If minority carrier comes here, the force experienced by a minority carrier depends upon the number of ions. If more number of ions are there, then it will experience a larger attraction. Okay. So, it depends upon the density of the ionic layers, or the number density of ions should be taken into account to calculate the minority carrier current, right. Let us now move on to the summary session. The junction diode equation is obtained using Poisson's equation. The ultimate junction diode we are yet to obtain, but the Poisson's equation is the one which should be used to evaluate the potential theta 1, theta 2 and the contact potential theta naught, and the width of the p-n junction or the ionic layers depends upon the concentration of dopants. The width of the ionized layers extends deeper into that region which is leastly doped. This is very important. The width of the junction region depends upon the concentration. It is again a very important point which leads to the tunnel diode, right. So, the questions are, what is the use of the p-n junction diode equation? You have the junction diode equation, what is its use? Whether the width of the depletion region will be the same on either side. What happens to its width when it is heavily doped? With this we come to the end of lecture 13, and in the 14th lecture we will eventually obtain the junction diode equation or the rectifier equation. With this we end lecture 13. Thank you.